Hello and welcome to my dual degree project presentation. My name is Parth Deshpande and the topic of my project is vehicle path generation and tracking in mixed road traffic. This is the outline of the presentation and the work itself is divided into two parts, trajectory generation and trajectory following. Starting with a brief background, as we all know, India has a very high number of accident-related deaths, which is over 11% of the world total. And there are a lot of driver assistance systems which have been developed already for vehicles, but the issue is that most of them are not specifically designed to work in disordered traffic conditions like those we see in India. Hence, there is a need to model the motion of a vehicle in such traffic conditions. If we look at some existing models, we see that the traffic models, which are in the upper half of the table, typically predict vehicle motion without considering a trajectory or the dynamics of the vehicle. And on the other hand, vehicle models, which are in the bottom half, do not consider disordered traffic scenarios. If we also look at some common control strategies, we need to look for one which is robust and gives good performance while not being too computationally intensive. So based on these ideas, the aim for the project is set as to develop a model which can generate and follow a vehicle trajectory in mixed road traffic conditions by considering the surrounding traffic environment, and it would give the steering angle as the control input to the vehicle. So the vehicle speeds here are assumed to be low to better represent urban traffic conditions. This flowchart here represents the steps involved in modeling vehicle motion, where we are only concerned with the lateral motion as highlighted in green, and the other aspects are longitudinal motion and data-based models which are outside the current scope. Moving on to model development, so the first step here is to understand the surrounding environment of the subject vehicle, and we assume that the vehicle here interacts with traffic in two regions. One is the detection region, which is based on the visibility range, and the other is the collision region inside it, which is based on the safe gaps to be maintained. So based on these regions, we define a leader vehicle, which is chosen as the slowest vehicle in the collision region as it has the highest risk of collision. And if there is no vehicle in the collision region, it is chosen as the diagonally closest vehicle in the detection region. So once we choose the leader vehicle, the next step is to decide on a desired waypoint. And the y coordinate of this waypoint is based on the fact that a safe lateral gap has to be maintained with the leader vehicle at the end of the overtake as shown in the figure. This is also represented by equation 1. And for the x coordinate, we have a minimum and a maximum constraint. So the minimum constraint is based on the highest curvature of the trajectory, which in turn is based on things like the lateral traction, the steering angle limit, and even rider comfort. And once we have the maximum value of the curvature, we can get the minimum allowable value of the x coordinate, and this is from equation 7. So the maximum possible value of the x coordinate is obtained based on the objective that the overtaking should be completed before the subject vehicle reaches the leader, and this is to avoid a collision between them. So this means that the relative distance covered should be less than the gap between them. So once we have these two values to generate the trajectory, we compare them and we say that the trajectory is feasible only if the maximum value obtained is greater than the minimum possible one, else the overtake is aborted. So if it is feasible, the trajectory is generated as per equation 11, where the initial heading angle of the vehicle is theta I and the final heading angle is assumed to be 0, and this is to make sure that the vehicle is aligned with the road at the end, and these two here are the two boundary conditions. So the overall simulation is shown in the figure, where the outer loop consists of the decision models and it has a larger time step of 1 second as they are more computationally intensive, and the inner loop is the control loop, which has a smaller time step of 0.001 seconds, and this is for accurate control of the actuators. So moving on to trajectory tracking, here we take a standard lane following model and we modify it to suit the purpose. So there are two error variables involved here, E1 and E2, which are the lateral deviation and the heading angle deviation at the current point respectively. Moving further, the final error variable considered is the look ahead offset YL as seen in equation 30, which is basically the predicted lateral offset at a distance ds ahead of the vehicle if it were to just continue moving straight without doing any maneuvers. And in order to find YL, we need E1 and E2, which are calculated using simple geometric relations. So the expressions of E1 and E2 are obtained and shown here. Moving on to trajectory following itself. So the vehicle dynamics here are modeled using a dynamic bicycle model, which is a reasonable approximation of lateral vehicle dynamics at low speeds. And the vehicle parameters here are taken from IPG car maker. So this is a vehicle simulation software. So further, we design 4 types of controllers here for trajectory following, and the first one here is a PI controller which is designed for performance. So the specifications used for designing are a 10% maximum peak overshoot and a 1 second settling time, as that is the time step of the outer decision loop. Now the ratio of integral and proportional gains is assumed to be a very small value, and the transfer function is then modified accordingly, which is shown in equation 21, and the gains here are obtained by using the root locus method. The next type of controller designed is a P controller for robustness, and here we use Pareto's theorem. So Karatnov's theorem states that if the four Karatnov polynomials, which are shown in equation 23, result in stable systems, then any system whose parameters lie within these bounds would be stable. So the next task here is to find the limits on these vehicle parameters. So the first parameter here is the cornering stiffness, which is based on the normal loads on the tire. So for finding the limits, we use the dynamic load transfer property as shown in equations 24 and 25. So it says that some portion of the load on the rear wheels would be transferred to the front wheels during a braking maneuver. So this gives us the limiting values on the normal tire loads, and it is further used to find the limiting values of the cornering stiffness. Moving on to the mass, so it is assumed to vary from that of an unladen vehicle to a laden vehicle, and the mass distribution is assumed to remain the same, so which is why the moment of inertia does not change much. The speed we consider it to vary from 15 to 25 km per hour, and if we have larger variations there, it may result in a bifurcation which causes system instability. So based on these limiting values, we define four plants P1 to P4 based on the Karatnov polynomials, and we obtain a range for the gain which stabilizes all the systems. So the upper bound here, which is 0.561, is chosen, and this is to reduce the effect on the performance. So as we saw here, PE and PI controllers can either be designed for robustness or for good performance, but they can't do both together. So this serves as a motivation to try out sliding mode controller, which drives the system states to the equilibrium point via a sliding surface, and the sliding surface is shown in equation 27. So a reaching law is used here, which takes the states to the sliding surface and then slides them along the sliding surface. And one of the standard reaching laws used is the constant reaching law, which is shown in equation 30. But an inherent issue here with SMC is chattering. So chattering is basically rapid oscillations, and it can also damage the actuator. So to eliminate this, one of the methods is to change the reaching law. So the first method here is using a boundary layer method, where we replace the signum function in the reaching law by a saturation function. So what this does is that it converts the sliding surface into a band, so that the small error values which are causing oscillations are neglected, and this in turn eliminates chattering. The control input here is found using the system dynamics, so it's shown in equation 33. But an issue here is that since the sliding surface is converted into a band, there is no ideal sliding behavior. So this can also be a cause for loss of robustness. Now the other method here is using a new power rate exponential reaching law. So it has a power rate term, which is the k by n term. So this makes the gain adaptive, which means that the gain is reduced as the states approach the sliding surface, and there is an exponential term s power beta, which helps in maintaining the sliding behavior. So this combined helps in maintaining robustness while reducing chattering, and the control input is found similar to the previous method, which is shown in equation 36. So based on these formulations, let's move on to the results. So here the trajectory generation and the trajectory following models are simulated separately. Now this is because currently there is no solution which can integrate traffic and vehicle models accurately. So the trajectory generation model is tested in a simulator which is developed in MATLAB. Now the red box here shows a traffic vehicle, which can be a bus or a truck, and the blue box is the subject vehicle, say a two-wheeler. The surrounding green box is the detection region, and the black area right in front of the blue subject vehicle is the collision region. So in the first stage, the subject vehicle detects that there is a vehicle in its detection region and it initiates a maneuver. In the second stage, that is an intermediate one, so we can see that the maneuver is happening. And finally, in the third stage, the maneuver is completed and the traffic vehicle goes outside the detection region, so the subject vehicle just continues moving straight. So these are the overall trajectories obtained for both the vehicles with a successful maneuver. Moving on to the controller simulation, we do a co-simulation of Simulink and IPG car maker. So the controllers are first tested independently, and then we compare them using some standard maneuvers, which is the ISO double lane change test and the slalom test. And finally, we evaluate the robustness by changing the plant parameters, which are shown in the table. So these are the initial results, which are more or less similar for all the methods, only the overshoots are varying between them. However, if we see in the sliding mode controller with the constant reaching law, we can see that chattering is occurring here, so it is actually detrimental, and hence we eliminate this method from further testing. The other SMC methods here perform as expected. So the first stage of comparing the controllers is a standard ISO double lane change test, where the red triangles are the cones or the boundaries, and we can see here that the robust P controller overshoots a lot and it results in a collision with the cones, while the other controllers perform more or less similarly. The next stage is a more intensive slalom test, which has a zigzag maneuver, and here we can see that even the performance driven PI controller has more overshoots, and on the other hand, the two SMC methods are performing as expected. So the final stage of testing is the robustness evaluation. And with the robust P controller, we can immediately see that all the trajectories for all the plants are resulting in collisions with the cones. And this is basically due to an insufficient gain, which results in a lack of performance. Moving on to the PI controller, it fares better, but the variations in the overshoot are still high across plants, and some of them are getting too close to the red cones. Now the SMC with the boundary layer method, which is the saturation function, it performs well, but there are still slight variations. And also in this case, the robustness cannot be guaranteed for the limiting cases. Now this is because there is no solid condition which is obtained based on Lyapunov stability. Moving on to the final SMC with the power rate exponential reaching law. This performs well and it has a good response time as well. The only drawback here is that it has a slightly higher control action, but it is still within the limits of the actuator, so it is fine. So summarizing all these results, the contributions of the current work are that we have integrated vehicle and traffic models for the first time. We have adapted a lane keeping model which has been used for trajectory following. We have applied suitable checks based on the driver and vehicle constraints. And we have also developed 4 kinds of controllers. We have implemented them and we have evaluated their performance based on the robustness. And the conclusion is that SMC with the PRERL has turned out to be better performing. The future scope here includes consideration of high-speed dynamics and different traffic scenarios, and a disordered traffic simulator can also be developed based on this for testing autonomous vehicles or ADAS models and so on. So this is the visible output from the work, and we do have another journal publication in the pipeline. These are the references for the work. And these are the appendices for reference. So the first one here contains the matrices of the state space model which is used, and the second one has the vehicle parameters. So this concludes the presentation, and the report itself is organized similar to the flow of the presentation with the chapters shown here. And thank you very much for your time.